With that, I'm very happy to bring on screen Elizabeth Rossi from External Affairs at Google Quantum AI. We love having the Google Quantum AI people speak in this series. They are not only brilliant, as you would expect, but they are articulate. They explain quantum computing so well, and the high-performance computing community in particular can't wait for quantum computing to be one of the new performance modalities of HPC. So Elizabeth, welcome, and thank you for coming on.
Thank you, Jay, for such a warm and kind introduction. I'm going to go ahead and share my screen. Okay. Hopefully you all can see that all right. Maybe a thumbs up in the Meetmoji to test it out. Awesome. All right, well, good morning, everyone, or I guess good morning, depending on where you're joining in from. My name is Elizabeth. I am part of Google's quantum computing team called Google Quantum AI, and I work on our team's external and government affairs, so a lot of the engagement, collaboration, and external strategy work that we have. Thank you for having me here. I'm really looking forward to talking to you all about what quantum computing is, what Google is doing in quantum computing, and sort of why we are doing it. I always think it's very helpful to ground ourselves and start with that question of why. Why build a quantum computer at all? With increasing data centers and AI and classical computing tools, do we really need a new type of computing? And what added benefit would it have? Are there certain problems that can't be solved by existing computing today? And the simple answer is yes. And I think one interesting way to think about that answer is with this quote from Richard Feynman here, where he says, nature isn't classical, damn it. And if you want to make a simulation of nature, you better make it quantum mechanical. And this is a quote, if you've heard from anyone from our team speak, it sort of consistently comes back to us. And to me, this means, whether we know it or not, we are surrounded by quantum mechanics in nature. And many things are made up of molecules, electrons, and operate quantum mechanically. And even with today's best AI and classical tools, it's very difficult to calculate, model, or simulate many things in nature classically. So we can, try to estimate or make broad calculations, but there's a lot we can't understand exactly using classical techniques. So for example, how molecules are behaving at their fundamental level, how they may interact with one another, how they behave in their excited state, and so on. And if we can understand these things better, we can understand more in nature, and from there solve problems that are just not possible using classical computing today. So I'll touch on a couple concepts that make this possible, and apologies if this may be already familiar to some of you, but I think it's helpful to just briefly review. So quantum computers are fundamentally different from classical computers. They are not going to replace classical computers. They are good for different types of problems because they are very different types of machines. Classical computers manipulate information using binary rules, zeros and ones, on or off. Quantum computers, on the other hand, use the principles of quantum mechanics to do some interesting computing techniques to store and process information. But just like any other computer or any computer, they're built from fundamental units of information. So in a classical computer, that unit is called a bit, which, like I mentioned, is either represented by a 0 or a 1. And it can only be one of those states at any given moment, like a light switch on or off. In a quantum computer, however, we use something called a quantum bit or a qubit. And unlike a traditional bit, a qubit can be both a 0 and 1 at the same time. This is due to a property called superposition in quantum mechanics. And because of this property superposition, quantum computers can simultaneously represent and explore millions and billions of combinations or pieces of information, which is, a dramatic leap from the classical computing ability to process only one by one. So if we try to think about, the power of this. So for very simple problems or basic tasks, the time it takes for a classical computer and a quantum computer to find a solution might be quite similar. However, when the size and difficulty increase of that problem, you see a bigger leap in problem-solving speed and ability. And because of this idea of superposition, if we look at n qubits, that doesn't just represent one state. That represents a combination of 2 to the n components simultaneously. And as you add more qubits and increase this n, that processing power scales exponentially. So that allows us to tackle massive data complexities that classical computers would take very, very long time to compute. So our overall thesis around this is that quantum computing will be a powerful tool for computation for solving certain kinds of problems. And here are a few of these problem areas where we expect quantum computers to have these advantages. Beginning with and building on this idea of simulation. So like I mentioned earlier, there are many molecules, but also chemicals, materials that may be better understood using a quantum computer and have exponential speed up compared to classical methods in doing so. Quantum simulation will sort of come back to this topic, but it has applications in several areas, for example, industrial catalysts, batteries, solar cells, fusion energy, drug development, and more. Beyond simulation, there are other classes of problems such as factorization we see here. This is an area that gets, a lot of attention, and because at a high level, the idea here is that our current digital security relies on the fact that classical computers find it very, very hard to do factorization at certain levels. A quantum computer, however, can do factorization a bit easier and quicker than a classical computer would. So in a post-quantum world where we have these large-scale quantum computers capable of these types of problems, we can no longer rely on factorization in the way that we do today for encryption and cybersecurity. There's also differential equations, quantum machine learning, unstructured search, and other classes of problems that are predicted to have these speed ups with quantum computers and other potential applications in many fields that we'll come back to in a bit. So building on this thesis, our mission at Google Quantum AI is to build quantum computing for otherwise unsolvable problems. And to sort of help organize this goal and the industry overall, Google published this roadmap back in 2019 on how we plan to actually achieve building a large-scale quantum computer. It's broken down into these series of milestones, beginning with milestone 1, which was in 2019. This was when we showed for the first time that a quantum computer can solve a problem much faster than a classical computer. That problem was an algorithm called random circuit sampling, and you can kind of think of this as like an algorithm the industry uses as a benchmark to measure the speed up of quantum computers versus classical computers. And in 2023, we demonstrated what we call a logical qubit prototype. This milestone 2 demonstration showed that as our errors began to decrease and the overall system performance got better as we made our system bigger. So we showed a prototype of what we call a logical qubit. And this is a concept of when multiple physical qubits can be sort of grouped together and work together and encoded to form a single, more reliable logical qubit, showing improved error rates as the system scales up. And this is something we will come back to. We are now here on our journey on our way to milestone 3 to demonstrate a long-lived logical qubit, one that scales this concept of milestone 2 further, making the system bigger and more reliable. And then scaling up to our final milestone, milestone 6, a computer with what we predict to have about 1,000 logical, well-protected qubits that stay reliable for long enough to solve these large-scale problems. And if you're seeing this roadmap for the first time, this may not mean as much to you, but I still wanted to highlight like where we are on this roadmap and how our thinking has evolved since 2019 when we first put this out, with this phrase, M5 is the new M6. So this really just shows an update to how we're approaching scalability and some of our future milestones. Innovations in software, error correction, computer architecture are actively decreasing the resource requirements needed for fault tolerance. So this means our path to running these commercially viable quantum applications is becoming shorter and more resource efficient than what the industry projections initially suggested, which is great. To speak to one of these areas of innovation, I would like to introduce the concept of errors and therefore quantum error correction. So qubits are notoriously sensitive. They are prone to environmental noise, and errors can be triggered by almost anything, from microscopic defects in the physical material of the chip all the way to a stray cosmic rays passing through the room. And as you can imagine, we can't completely shield a computer from all of these forms of error. So our software and our architecture sort of have to be smart enough to detect and correct these disruptions in real time. And that's where quantum error correction comes in. So quantum error correction is a very important concept. It's vital to building a fault-tolerant quantum computer. So bear with me as I just explain it for a moment. And I think one way we can think about this concept is through a measurement called gate error probability. And that's shown here on the left. So a 10 to the -2 in gate error probability means you're making one error in every 100 gates. And you can kind of think of gates as like operations. So one error in every 100 operations. Then going down to 10 to the -12 in gate error probability means you'd make only one error in every 1 trillion gates. So only one mistake in 1 trillion operations, which of course is far better. Physical qubits today are in this 10 to the -2 regime. And there has been, a ton of hard work to get there. However, that is like nowhere near where we need to be able to reliably run real-world practical applications. And again, this is where quantum error correction comes in. It helps us encode and entangle information across multiple physical qubits. They kind of form these like groups that can work together to form a more robust logical qubit, which how we would title like that group. And that allows us to dramatically reduce this overall error rate. Willow is our newest generation of processors that has shown and demonstrated some major system improvements and allowed us to demonstrate some key advancements in this field of quantum error correction. And I'd say this is an important thing to highlight because it sort of represents the current state of the industry and currently sets the bar for some of the beyond classical demonstrations that we have today. And this generation of processors, Willow, are uniquely suited for quantum error correction. With Willow, we were able to make a first ever demonstration of error correction below threshold. So without getting too focused on some of the details on this slide, we showed that errors can be suppressed below a critical threshold. And below this threshold, as we make our system bigger and add more qubits, we are actually decreasing our errors exponentially. And like I mentioned earlier, qubits are notoriously sensitive. So in the past, adding more qubits would just make the system more complex. But in this case, we basically showed the opposite, that adding more qubits actually improve our system reliability. And this was the first experimental demonstration of showing we can actually exponentially decrease our errors as we add more qubits. And this was a huge achievement for the industry because you can kind of imagine, below this threshold, we can sort of future-proof our scaling because now we're saying, okay, we can scale and add more qubits and make our systems bigger, while the quality is actually getting better and better at an exponential rate. And to put this in perspective a bit on where we go next from some of these demonstrations with Willow and what our team is working on now. So what we're looking at is a graph of this error rate on the y-axis and number of qubits, or the size of the system, on the x-axis. We're here, or I guess a little bit past this at this point, with the line labeled Willow. And our next goal is to better our error even more, our error rates even better, and also scale the size of our system, represented by the longer blue line labeled as our next milestone, where that line gets longer, so more qubits, increasing the size of the system, and lower, so a better error rate. Okay, so we have a bit of background on some of the critical concepts behind quantum computing and architecture of error correction in a general sense. But a natural question is, like, how is the industry actually building this physically? And as you can see on this slide, there are different approaches to building a quantum computer. You can build and manufacture your qubits using different techniques. And here's a number of them here. It's a very interesting time for the field. I think, like, each of these approaches sort of have their pros and cons. Google is invested in superconducting qubits, and we are very confident in this approach and its path forward. However, there are other ways of building quantum computers. And superconducting and neutral atoms are sort of the two platforms that have demonstrated closest to practical fault tolerance at this point. The benchmarks on this slide really just show how both architectures are, going back to this point, are rapidly suppressing errors and hitting these major scaling milestones. But again, like, each of these approaches sort of have their pros and cons. For example, superconducting excels in things like gate speed and deterministic control. We can manipulate them incredibly fast on a chip. Neutral atoms, on the other hand, excel in natural stability and physical scaling. Their drawback is that their gate operation is a bit slower. But looking at them side by side, you can imagine how they complement each other's weaknesses a bit. And this is why Google recently announced we are expanding our quantum computing research to include neutral atom computing alongside superconducting. And the way that we're sort of seeing this is, investing in both approaches basically just increases our ability to deliver on our mission sooner. By advancing both, we sort of cross-pollinate these pros and cons and the research and engineering breakthroughs, and can deliver access to versatile platforms tailored to different types of problems that would benefit from these pros and cons. We remain very confident in our approach in superconducting qubits and its path and roadmap forward, and we are now expanding to also include neutral atoms. Okay, so switching gears a bit, maybe to the fun part, like, what can we actually do with quantum computers today and in the future? So a natural question may be, how do we actually measure the progress to practical applications on quantum computers? And one of the ways of doing so is using a benchmark that I previously mentioned, this benchmark for beyond classical performance called random circuit sampling. And again, this is sort of this is the same benchmark we used in milestone 1 in 2019. And you can think of this as an algorithm the industry uses that's, like, very hard and specifically designed to measure the speed up of quantum computers. And we can measure Willow's algorithmic performance using this benchmark, for example. So we reran this algorithm with Willow because since 2019, classical computing and supercomputers improved, and so did quantum computers. So we kind of wanted a more accurate and current benchmark today. And what we found is that Willow can solve this problem in 5 minutes, where the world's fastest supercomputer, we used Frontier, would take 10 septillion years, which is a really big number. It's 10 with 25 zeros, which is a number that's hard for me to comprehend. It is beyond the age of the universe. So a very long time. And this achievement, not only shows sheer compute power, but it also shows a rapidly growing gap between classical and quantum computation. But it may be hard to imagine hearing that number 10 septillion. We are still in early stages. So current quantum computers can almost be thought of as like a prototype. They are not large or reliable enough yet to tackle these large-scale commercially relevant problems that we hear about. However, our current prototype level processors are still being used for very exciting scientific discoveries. Here's a splattering of some of the areas that we've used our current processors for, and you can see a lot of which are inherently quantum mechanical systems, like understanding wormhole dynamics, for example. And we are getting closer and closer to real-world commercially relevant application. One application I would like to highlight was work we recently announced this past year called Quantum Echoes. So Quantum Echoes is an algorithm that can help us simulate and understand quantum systems. So going back to this simulation idea previously. And we showed that this algorithm is beyond classical, verifiable, and useful for real-world applications. So meaning it runs on Willow 13,000 times faster compared to the best classical algorithm on the world's fastest supercomputer. It can be repeated by another quantum computer to actually verify the result. And that might sound simple, but that was actually a first. And can explain interactions between atoms in a real-world molecule with potential for real-world application that we'll double-click into. So more specifically, we showed that quantum echoes can be used to better NMR technology and map molecular structures with greater precision. So NMR underpins MRI technology you may have heard of. It's a method that's widely used to image and analyze the internal structures of complex systems. And quantum echoes allows scientists to just get a much clearer, high-resolution view of the molecules that they are studying through NMR. And this improved capability sort of provides a more powerful tool with direct applications in areas like materials science, drug discovery, and advanced chemistry. Expanding on that capability even further, we can scale these tools from being able to look at individual molecules to more complex biological systems. So ranging from viral proteins to small molecules, drug binding, and target protein systems. In each of these cases, the primary bottleneck for scientists today is accurately modeling how these structures interact at a quantum level. And by utilizing quantum computation in this example, our goal is to simulate these complex behaviors better, going from sort of like rough approximations or rough views to more exact predictive modeling for some of these systems. And to just sort of take a little bit of a step back from there and put this in perspective on where we are today and how we think about applications a bit more broadly. So this is a graph showing on the x-axis how useful or commercially relevant an application is versus the y-axis, which is how classically intractable an application is. So how hard is it to do on a classical computer versus a quantum computer? So for example, this random circuit sampling I described as the industry benchmark used with Willow and in the past in milestone 1, this is an example of something that is like clearly practically impossible to replicate on a classical computer unless you somehow had beyond the age of the universe, but it is not a useful application and can't be used for anything commercially relevant. It is purely a benchmark algorithm. Quantum echoes was, we said classically intractable and on the verge of being very, very useful in these applications that we just learned a bit more about, but there's still some work to do there. So we can't fully, put it in the useful category just yet. So where we are heading and working towards naturally is this upper quadrant of what we call quantum benefit. And this is an application that is commercially relevant, so has some real world advantage and application, and also practically impossible to replicate on a classical computer. And the industry has yet to show this. But a lot of these, system improvements that we saw through Willow and this new generation of processors really allows us to have a system capable of doing this and gets us closer to that quadrant of quantum benefit. I'm glad you like the term. And the applications we expect to fall in this area, we are already working on with a number of partners. Here's are some examples. Things like, drug discovery, battery design, industrial catalysts, similarly in this area of quantum simulation. And, as you can see from some of these application areas, this isn't work that we can just do like in a vacuum at Google Quantum AI. Partnership is critical when it comes to practical quantum applications. We need to pair these domain experts, so the biologists, the chemists, the material scientists, who deeply understand these problems and these systems, with the quantum experts on the hardware and algorithm side. And that collaboration is, really how we solicit and uncover new areas of impactful research and therefore, impactful applications of quantum computers. An example I'd also like to highlight in this area, one program that we're kind of excited about that we recently announced is REPLICA, which stands for Research Program at the Intersection of Life Sciences and Quantum AI. REPLICA is a new quantum-focused initiative designed to do what we've just described. So, catalyze scientific discovery by applying quantum engineering and AI to the life sciences in this case. So to kickstart this effort, Google is committing $10 million in initial funding to support these research activities across 5 university partners here. And you can kind of see through this example, and there's other examples, not just with academia, but other industry partners and whatnot, that bridging, in this case, academia and industry in this way, we can sort of move from these theoretical use cases and progress on the hardware side into validated breakthroughs in applications. And that brings me to some of my final few remarks on sort of the broader picture for the industry and the challenges and therefore opportunities ahead. Finding and validating these practical application areas is one of these opportunities. I think there'll be an increasing amount of discovery here, and we haven't discovered the extent of how we'll use quantum computers. But in addition to this, as we look ahead, there are a host of challenges. Of course, the technical challenges, which could be like a whole presentation in itself, actually building and scaling these systems, finding useful applications, but also the economic and ecosystem challenges. So for example, creating a robust supply chain. These are very complex systems that we're building with specialized parts, ensuring industrial adoption and that the industry is ready to actually use these systems. Of course, like investment and funding, and creating and sustaining the workforce that we actually need to achieve these goals. But I'll finish us off with going back to a quote from Richard Feynman, which again is another quote that our team often goes back to, where he says, "By golly, it's a wonderful problem because it doesn't look so easy." It certainly doesn't look very easy. It hasn't been very easy, but we've made a lot of progress thus far, and very excited for more specifically, the couple of years ahead will be very exciting and beyond, of course. So thank you for having me. I'm happy to take some questions.
All right. Thank you, Elizabeth. And everybody give Elizabeth some applause with the meat emojis there. And Elizabeth, I'm going to pull up the Q&A here, and we have 5 questions in there right now. I'll ask as many as we have time to, and hopefully some additional ones will be submitted. All
Sounds
right.
great.
I saw a question that Miguel put in chat, asked him to put it in Q&A, and he did. So I'm going to start with that. Miguel asks, can you please explain more in detail the concept of code distance?
Yes, that's a good question. And I actually, as I was going through that slide, I noticed that, code distance was on it and I didn't really address it. So thank you for bringing it up. Code distance is pretty much, it dictates the number of qubits. So it's proportional to the number of qubits that we have. So the details of how code distance is determined gets a little bit technical, but its main dependency is the number of physical qubits. So you can kind of think of it, when we were looking at some of those graphs, like code distance represented the size of the system, because it's almost equivalently proportional to the number of physical qubits. And the underlying sort of principles for how the code distance number is determined from physical qubits is based off of, again, this concept of errors. So the number of physical errors a single code can detect or correct. But for simplicity, I would say like it's proportional to the number of physical qubits, so you can kind of think of them similarly.
Miguel, if that answered your question, can you give us a plus sign? Or if not, you can give us the dreaded crab. Give us the plus sign. All right.
All right.
Bill asks, amazing work. Around the same time last year of the amazing Willow announcement, Harvard was having great success with a hot swap approach, swapping in new qubits as they would decay. Is this something that can work together, presumably with your error correction approaches?
Yeah. I have to admit I'm less familiar with the hot swapping approach, but I think like more generally, yes, this is like a concept that can work together, where we're kind of getting at, quantum error correction almost uses its qubits to correct each other. It's kind of a sweet concept that, qubits can kind of work together in a group and look out for each other and correct themselves and detect errors themselves. But then there's another form of suppressing errors where, you actually replace qubits, or you sort of come into the system rather than letting the qubits sort of do it themselves. And yeah, I think there's a world in which the combination of being able to detect and then suppress, physically, while also having robust error correction to do it themselves as well, would probably be compatible. Yeah.
All right. And Tori Battelle asks, what is the classical analog of the gate error probability, or what is considered the classical error rate?
That's a good question.
I can probably help a little bit with that one on the classical side, Elizabeth. So we already have errors that affect memory, which is why we have error correcting memory. And just the error rates are so low that we don't really even call it ECC RAM anymore. Most people just call it RAM, but it's got error correction built in, but the number of redundant bits it needs is incredibly low because the error rates are so incredibly low. Likewise, GPUs have had error correction capability in their internal circuitry and memory for a long time as well. And there used to be an era in which you had GPUs for gaming systems that didn't have error correction because you wouldn't even notice if one pixel was off in a 30 frames per second shooter or something like that. Right. But for data center GPUs, that error correction is absolutely important. It's just that in classical, the error rates are so low that you don't need nearly as much error correcting overhead circuitry as well. Whereas these quantum bits, as Elizabeth explained better than I can, are so sensitive that you're much more likely to get perturbed by environmental conditions.
Yeah, thank you, Jay. I think like it also sort of highlights, again, we're at early stages in quantum computing. So comparing something like, error probabilities now is going to be very different than maybe 10 years from now. And maybe it'll be less of a focus of a presentation I would give you. But yeah, we hope that those error rates develop in a way that it's less of a focus of our research. But
Joseph asks, what is the connection between quantum computing and AI? Why is the lab called the Quantum AI Lab? I bet you get asked that question a lot.
Yes, I was going to say that is a great question. I always get it. I think like the high level answer is Google sees quantum and AI eventually working together. Right now, we are a quantum computing team, but some of the initial reasons we were even founded by our founder, Hartmut Nevin, was because he was interested in some of the potential applications in AI and how quantum computer can better AI and AI can better how we're building a quantum computer. There's a number of ways in which we're exploring that. I briefly mentioned, quantum machine learning being one of them. Maybe I'll just chat about that for a moment. So most classical machine learning models struggle when tasks require processing data with very complex non-local correlations. And the example that we've been using that I think is the strongest example is modeling the behavior of molecules or quantum materials. So quantum machine learning is an example of something that aims to use quantum hardware to capture these patterns and create more accurate and computationally efficient predictive models. So you can kind of think of it as in this case would be a specialized tool for specific high complexity problems. A key area of some of our recent research within this is focused on using quantum computers to generate vast amounts of high quality classical training data. So you can use a quantum processor to simulate quantum systems and generate these synthetic data sets that classical computers can then use to train standard machine learning models. So, that's an example of basically this going back to this point that we see quantum and AI working together for specific problems. Quantum will be better than AI for certain problems. AI will be better than quantum for certain problems, and there'll be some that are better together. So that's sort of why we're called Quantum AI. I think, again, a lot of it goes back to the initial interest in quantum computing in its applications in AI. And again, our founder, Hartmut Nevin, has a strong background in AI. So that was a particular area of interest. And in the long term, I think, Google sees them working together.
Related question from my buddy Skander. Quantum ML is theoretically fascinating, especially the latest results on quantum advantage for ML problems with very high geometric complexity. But given the size of the data sets in typical industry ML application, is it realistic to expect QML to be useful for any real world use cases?
Yes, good point. I mean, there's a lot of research that still needs to be done on exactly what types of problems this would be applicable for. But it does prove out that quantum processors can be efficiently generate and learn from physical complex states. And those physical complex states have applications in a number of areas that we sort of touched on. I think like the most promising areas that we are internally invested in and exploring more are accelerating discovery in material science and chemistry, for example. So yes, we do see them as promising avenues in quantum ML.
All right. We have an anonymous question here. How will the co-development of neutral atom and superconducting qubits work at Google, considering how different the two architectures are?
Yeah, that's a great question. So, we're still figuring out a lot of the details. We will have, it'll be somewhat of an independent effort in some cases. Of course, like you mentioned, the hardware is fundamentally different. So the way that you're actually building out the hardware will be separate efforts. However, there's a number of areas of research that we have at Google Quantum AI, which maybe I can just spend a minute talking about. So quantum AI is a full stack effort, meaning, we have development on the hardware side, so actually building the systems, and that includes like the cryogenics, the electrical engineers, wiring, everything on the hardware side. We also have a software team. We have a applications and algorithms team, and we have like a physics modeling and simulation team. So we cover the full stack of superconducting quantum computing. And within that stack, there are areas, again, where superconducting and neutral atoms will sort of sit somewhat separately, mainly on the hardware side. However, on like the applications and error correction side, they will work together, and those teams will collaborate. We have Adam Kaufman, who's going to be leading that effort in UC Boulder. So we're excited about what that's going to look like for the next coming years, and we'll be publishing more and more, as we develop that work there. OJ, I think you're on mute.
Oh, sorry, I had to go on mute because my GOOGLE home speaker heard me ask questions that had GOOGLE in them and decided to start answering them in the background. So a couple of follow-up questions to that. One, a long time ago, Google made an investment in QEra, which is a neutral atom company. Is QEra part of Google's neutral atom approach?
No, it still sits like separate as a corporate investment, but I think that shows, we've been following neutral atoms for a long time now. And that was an initial signal that we're very interested in the development of neutral atoms, and we see it as a very promising avenue. But no, that's sort of a separate corporate investment, but again, signals our interest in neutral atoms for quite some time now.
Okay, and do you want to make any comments about, unlike classical computing, where we basically make all chips on silicon wafers fundamentally the same way, exactly what we etch is different. NVIDIA etches something different than AMD, who etches something different than ARM, and so on. But these quantum modalities are all quite different from each other, and they have different error rates, different gate speeds, different coherence times, et cetera. Do you want to make any comment about superconducting qubits versus neutral atoms in any of those regards?
Yeah, sure. Yeah, so like each of these techniques for building quantum computers have their pros and cons. And I think, like I mentioned before, it's very interesting to see how each of them are developing. And I think it's, a lot of those pros and cons are still being weighted and are yet to be determined. I think most generally, just like almost like a words of advice, is to, because there are so many specifications that come along with each of these types of quantum computing, it's important to try to get a hold of as many specs as you can. So like, for example, we've been talking about this quantum error correction concept. That kind of highlights, the number of qubits is not the full story. So like you can see a headline that, X type of quantum computer shows X number of qubits, and that's not the full story. You sort of need to see the error, the speed, the fidelity, all of these things are important. As far as superconducting versus neutral atoms. So superconducting processors are easier to scale in circuit depth and are much faster in their operations and a bit more engineerable. And we have like a pretty good understanding of how superconducting processors work because we've been working on it for so long, and we feel very confident in our roadmap going forward, and have sort of made it a more of a engineering feat from here out. Neutral atoms, on the other hand, are easier to scale in the space dimension, so like the qubit count, and have some other benefits around, they're a bit less complex systems because of that. They don't require all the cryogenics that superconducting processors do, but at the same time, they're slower operations historically. So, again, these pros and cons. And again, having both sort of is the best case scenario because you can sort of cross-pollinate the research breakthroughs on the neutral atom side and the engineering breakthroughs on the superconducting side. And I won't get too into the weeds here, but certain applications will benefit from some of these aspects more. So a particular application might not need very fast operations, but it might need a lot of qubits. And that would be an example where it would benefit to have a neutral atoms platform. Whereas, the opposite, if it requires faster operations, then superconducting would be the way to go. So having both also allows to have versatile platforms tailored to different types of problems.
That's what I was hoping to hear. Thanks, Elizabeth.
Yeah.
Shishir Dua asks, can we go beyond 20 physical qubits with code distance at Google environments as of now? I feel like there's a word or two missing there. Can we go beyond 20 physical qubits with code distance at Google environments as of now?
I'll maybe just answer it as yes. Like we have far more than 20 physical qubits. And within a number of physical qubits. So if we're taking Willow, for example, we're now past this point, but we published 105 physical qubits, and within that 105 physical qubits, we measured at different distance codes, and both of which showed this exponential decrease in errors. So I guess I'll answer your question as yes, and we're past that point.
Awesome. We have time for one more question. We have a whole lot more questions. So Elizabeth, I'll work with you offline after to see if we can get answers. Maybe you can just verbally speak and we can let Gemini transcribe some answers so it won't use up much of your time, and see if we can share maybe those as well as your slides in a PDF format if Google Quantum AI is willing. We're getting requests for your slides. We're getting a lot of questions. This is fantastic. It shows a lot of people are interested in this. But let me ask the last question from my good friend Denise Holt. What is the plan to solve for decreased fidelity with increased depth of logical qubit? Yes, the error rate decreases with increased depth, but it introduces crosstalk and other issues that decrease fidelity. And full disclosure, I've been planning to introduce Denise Holt to the Google Quantum AI team at some point in the near future anyway. So I'm glad she's on this call.
Nice to meet you, Denise. It's a great question. I won't get too into the weeds here, but maybe I can follow up with some papers in this area. But this is definitely something we're thinking about. I mean, fidelity is incredibly important, and even with Willow and internally beyond that, our gate fidelity is quite strong. And there's a number of areas. A part of our team is focused on things like crosstalk and worrying about that type of error. And we've done a good job. I would encourage, this is part of our Willow announcement as well. So there's some material that's public there. And we also have some papers on crosstalk. But good to highlight that this is an area that, of course, we care about. And we are doing a quite a good job. I'd say like the Willow processor, again, going back to this point of there are many specs to consider. This is definitely one of them. And I think the Willow processor across the board doesn't have anything that's like totally weighing us down. So that's great. And Fidelity is included in that. That's not something that is weighing us down at this point.